I originally made this product evaluation video on this Airbit drone here a few months ago for an entirely internal purpose. The original people that were supposed to watch it had some prior context to what they were watching and why. Because of that, not everything in this video will entirely make sense, but I've done my best to slim it down and only keep the relevant bits in. Refer to the chapter markers if you want to know where to go to in the video to skip the boring bits. The first half of the video is an evaluation of the product and how I think it both succeeds and fails to fill its goals as an education kit for teaching programming to kids. The latter half is where I dig deep into the technical workings and discuss how low-level firmware development works on embedded hardware and how I flashed it with custom Homebrew software. The Airbit 2 by the Norwegian company Make-Kit is an education kit targeted for classroom STEM programs to teach kids how to code. The Airbit is the drone entry to the WonderKit line of products. The Airbit uses two microbits at its heart for the drone and the controller. The BBC Microbit is an open source single board computer and software ecosystem targeted for STEM education with significant investments and contributions by Microsoft. To simply describe it, it's similar to an Arduino with some extra hardware. It's a low-cost PCB with a microcontroller, a few buttons, speaker, microphone, LEDs, RF, and various other sensors. To program it, you can use the online Microsoft MakeCode editor, which has a wide array of tutorials, and you can use a GUI drag-and-drop block programming interface. This editor is very similar and probably derived from other learn-to-code STEM education websites like code.org, Hour of Code or Scratch. Its visual style is made to teach basic concepts such as variables, loops, functions, if-else statements, etc. as universal building blocks that can later be adapted to real programming languages. Additionally, you can also view the code of what it would look like as JavaScript or Python. You aren't just restricted to these GUI drag-and-drop blocks. You can write actual code in the typical sense. To be clear, this microbit is an independent product and ecosystem and can be used on its own. Make-Kit is a separate company and is only making the drone hardware for the Airbit and packaging two microbits along with it. The programming portion of the Airbit is simply setting up the microbit on the controller to transmit roll, pitch, and yaw commands, and the other microbit on the drone to receive and act upon those roll, pitch, and yaw commands. Generally, when I refer to programming the Airbit, I'm referring to the BBC microbits, as that's the only part you actually interact with. Building the kit took me about an hour and a half. Most of that difficulty was getting the wooden motor plates jammed in without breaking, and to start I just flashed the provided example code to the controller and drone. Make-Kit describes building and programming time to be around 6 hours, and for a first-time builder that seems to be about right. To fly the drone, plug it in and leave it on a flat surface. When it first powers up, it will do a calibration procedure, which you can see on the LED array. On the controller, press both buttons at the same time to arm it. Press the right button to increase throttle and the left button to decrease throttle. There aren't gimbals, you control the drone by tilting the controller in the direction you want it to go. The microbit for the controller has an accelerometer and is transmitting the attitude to the drone for the drone to follow. The microbits on the drone and controller have an LED array which displays status info such as battery, throttle position, and the current roll and pitch. The video may not do a good job of showing this, but it's pretty difficult to fly and poorly tuned. It flies okay indoors, but outside and even the slightest winds is a challenge. The battery also only lasts a few minutes. Overall, the build is simple and it comes together easy enough. I see nothing out of place to put this on the store, but do keep in mind the drone itself is toy grade and is not in the same class as an FPV drone. The programming of the drone and controller is very simple. Just a few hundred lines of code. However, before understanding the limitations of that, it's important to understand the hardware of the drone. The drone itself has two boards, the microbit which you are programming and the control board. The control board is made by Make-Kit, which is a version of it unique just for the Airbit, and as far as I know is closed source, proprietary, and mostly undocumented. Everything in the drone plugs into this. The battery, charging cable, motors, and microbit. It contains the DC ESCs for the motors, a simple 1S LiPo charger, voltage ADC, servo pins which aren't used, IMU, which I'm going to refer to as a gyro, and an I2C bus. The motors and gyro share the same I2C bus. As far as I'm aware, I don't believe there is any firmware or microcontroller to this board. I don't see anything on the board resembling a microcontroller, and I don't believe the data pins of the USB port are routed anywhere. Every chip seems to be an IC, and I'm pretty sure the I2C bus is just the ESC and gyro I2C shared together, since both are acting as slave peripherals. There's only 5 pins going from this control board to the microbit. Power, ground, 2 pins for the I2C bus, and the last pin is the analog ADC for measuring battery voltage, which isn't required. The microbit is very simply reading the accelerometer and gyro data from the I2C bus out of the control board, calculating PIDs, and sending new throttle values for the motors back out of the same I2C bus. I'm not certain why the Airbit uses the gyro built into the control board, since it adds costs rather than the one already in the microbit. My guess is it has to do with leveraging the built-in hardware filtering of the control board's gyro, since it would have been too difficult to do filtering on the microbit's gyro. Basically, the microbit gyro wasn't good enough. The aspect I do not like about the Airbit is the programming experience of the microbits, and also the work done by Make-It on top of that significantly oversimplifies what goes into making a flight controller firmware. The reality is, 2/3 of the actual complicated stuff, such as the I2C drivers, PID controller, mixers, initializers, RF parsing, rate controllers, attitude estimators, and even some of the LED display, is already written by Make-It and completely hidden from you as an extension you have to install. Make-It themselves, in a comment in the example code you can write, describe it as magic. There is no magic, you just have to know where to look. In the code you do write, the core of the main loop is 4 function calls. One to get gyro data, one to get control inputs, and one to do the stabilization, and one to update the speed of the motors. The fault isn't only with Make-It though. The BBC microbit is even worse when it comes to oversimplification. Let's look at some code to do simple things like control the LEDs and display some text. Where is LED coming from? What is basic? This is supposed to be Python, but that is not valid Python because LED, basic, radio, and all of these other voodoo libraries are never imported but somehow in scope and initialized. The reality is you aren't really programming Python or JavaScript. You're coding in MicroPython or a similar fake micro JavaScript, and in the MakeCode editor that you use, it hides all of these library imports from you. The function that displays text on the screen by calling basic.showString is doing a lot under the hood. How did it know exactly what LEDs to toggle to make a letter come up on screen? And with that font. How did it know how to animate a sliding animation and to time it right? I never programmed that here, so who did? A lot is going on under the hood in this one function call. The problem with the microbit and the Airbit is that it massively oversimplifies the coding aspect with a lot of abstractions and drivers provided to you out of the box. 99% of the actual complicated embedded code is already done for you. You are just gluing together some provided functions into making this drone fly. I understand why it's like that. As an education kit targeted for children, the usage needs to be realistically graspable by anyone with zero familiarity with programming. It teaches basic programming concepts, but does not teach any underlying computer science principles. This is why I question the value and goals of this genuinely being a tool for education. I personally find this fault in many programming education programs and kits. Programming and computer science go hand in hand. There are programmers that don't understand computer science principles and as such are useless, and computer science students that understand a lot of textbook fundamentals but can't actually develop an end product, and as such are also useless. In the real world, you aren't going to be given finished hardware and have high-level libraries given to you to use it with one line of code. This is why this evaluation took so long while I try to figure out how to overcomplicate this. One of the ways the microbit tries to simplify the programming is by using languages that are very easy to learn, such as Python. The MakeCode editor has these graphical blocks, but you can convert it into Python, which is what those blocks translate to. So someone who is new to programming can have a much easier time getting started if they use an easy-to-learn high-level language like Python. However, Python cannot actually run on embedded hardware. Python is an interpreted language, not compiled. This means they require a separate runtime to work. Low-level languages like assembly, C, C++, and Rust compile down to actual machine code that CPUs can run, and is why they're almost exclusively used for embedded development. Python is very high level and it requires you to install the Python interpreter to your computer before you run it. There is no compilation process. Even the Python interpreter itself, which is written in C, is also heavily reliant on the operating system, like Windows, Linux, or Mac OS, to provide the POSIX API for things such as networking, file systems, console standard in, standard out, etc. But when it comes to low-cost embedded hardware like the microbit, these don't run Windows 10, they don't have networking, or file systems, or screens. So you can't just install the Python runtime onto it. But you can port a version of it, and that's what MicroPython is. A stripped down version of the Python interpreter that was made specifically to run on embedded hardware such as Arduinos. As such, it isn't nearly as capable, but the syntax is the same, so anyone who knows Python can jump right into MicroPython. And in fact, here's an example using an offline IDE, PyCharm, which has the MicroPython plugin and interfaces with the microbit to load code to it directly. Notice I'm importing the microbit library. This library exists on the microbit itself. When I run the program, the plugin just sends the Py file over to the microbit, and the microbit, with the MicroPython on it, stores it and runs it. It's not flashing firmware, it's basically just configuring it to run a new script instead. Additionally, you can also write in JavaScript, which instead of MicroPython uses a port of ESPrino as a JavaScript runtime. But it's functionally identical to MicroPython, so I'll mostly just mention MicroPython from now on. However, there's still a lot more going on under the hood than just MicroPython. To further understand the software stack of how this works, it's important to understand and overview the hardware of the microbit. A great resource for this is tech.microbit.org. This is development documentation of the internal workings of the microbit. It is not the make code simplified programming tutorials, but actual technical docs, and a lot of what I'm going to cover is what's already in these docs. The microbit has various sensors onto it, but at its core, it's just a microcontroller. However, unlike Arduinos, the microbit has two, the Nordic nRF52 and the Freescale KL27. Both are ARM microcontrollers just like STM32s. So why are there two? The Nordic nRF52 is the microcontroller that actually runs the MicroPython code. It also contains all of the low-level drivers, halls, and the code all runtime. You can even write Homebrew firmware from scratch to run on it, and that might be foreshadowing for what I ultimately do with this. Usually everything you do as far as programming goes on here. The KL27 is the so-called interface chip. It's kind of like a debugger similar to an ST-Link. It's basically just a middleman between the USB port and the target nRF52. The firmware it runs is a variant of DAP-Link. DAP-Link doesn't do much, but mostly just handles flashing the firmware hex files onto the target microcontroller. Since you plug it in through a USB port, it provides your PC a number of interfaces. One of them is acting as a virtual flash drive. If you plug it in, you'll see DAP-Link on this KL27 open up as a flash drive with some files that give some details of the firmware it's running. And normally, when programming the microbit, you drag and drop the firmware onto this drive, and the interface microcontroller will use it to flash the target microcontroller. It also provides a UART shell that you can write MicroPython to directly on the target microcontroller. The two microcontrollers are connected to each other by 3 different protocols. The first and most important is serial wire debug, which is a feature of ARM processors. This is a low-level debug interface, which among other things can be used to flash firmware to the target microcontroller. This makes sense because the target microcontroller does not have a bootloader. It doesn't need one since you never interface with it directly to flash firmware. The dedicated interface microcontroller handles all of the firmware flashing. There is also a UART link, which as far as I'm aware is only used to pass through the MicroPython shell out as a USB COM port. Lastly, an I2C bus. There is an entire detailed page describing this, but the short of it is, it just allows the target microcontroller to read some metadata from the interface microcontroller, and it isn't really important. This bus is also used to connect the target microcontroller to all the peripherals. The target microcontroller uses a separate I2C bus for the external I/O on the microbit. However, older microbits use a single I2C bus for everything. Lastly is the bootloader of the interface microcontroller. As mentioned, this KL27 interface microcontroller is what the USB port actually plugs into. The flash drive you see open up on your computer is provided by the main DAP-Link firmware, and pasting firmware hex files here will flash the target microcontroller. However, what if you want to write or update firmware of the interface microcontroller itself? You can do this by holding down the button on the microbit before plugging it in. Now instead of the flash drive saying microbit, it will say maintenance. This is the DAP-Link bootloader itself. And you can drag and drop hex files here which will update the DAP-Link firmware on the interface microcontroller instead. Now this DAP-Link bootloader on the KL27 is also a firmware and in itself can also be flashed. To do that, short the contact on the back here to ground while plugging in USB. This is now the lowest level hardware bootloader of the KL27, and you can now flash the entire firmware on it, either to DAP-Link or a custom Homebrew firmware. You will need to download the KL27's proprietary Beal host application to flash it. Keep in mind, all of this is just to show how to do it. You very rarely would ever have to flash it and update DAP-Link on this interface microcontroller, and there's basically no normal circumstance you would ever need to flash the bootloader as well. This is just a demonstration of why the microbit works like this. In general, this dual microcontroller designed for dev boards is common. This ST Nucleo 64 dev board and this Texas Instruments TVC Launchpad I have here work in a similar way. So we know that the microbit runs MicroPython code, but there's also a lot more software going on underneath. At its core, the firmware the microbit runs is written in C++ and called CODAL, also known as the microbit runtime. CODAL stands for Component-Oriented Device Abstraction Layer. Mostly the important part is the Device Abstraction Layer part of the acronym. Device Abstraction Layers, or DALs, are what provide the high-level APIs that do things like animate an entire sentence of text on the LED array with one line of code. You can even compile CODAL yourself and write applications within C++ instead of MicroPython, and you can still use the same super high-level DAL. When you write and install code in the web makecode editor onto the microbit, it flashes the CODAL firmware to the microbit packaged along with MicroPython and your MicroPython code. The MicroPython interpreter runs on top of the microbit CODAL runtime, and CODAL also runs on top of various other low-level abstraction layers. If all of this seems complicated, it's because it is. I'm not really going to go further into details of how the microbit firmware works. There's a lot of different technologies and softwares combined here, each with long histories. Ultimately, this NRF52 runs ARM machine code. If you can write in any programming language that compiles down to ARM machine code, it'll run. What I want to do is demonstrate flashing Homebrew firmware written from scratch that will run on this thing, to look past all of these complicated runtimes and layers of abstraction that hide the inner workings. Low-level embedded programming is an advanced field of computer science, and I dislike how the microbit and this Airbit drone tries to hide that from you for the sake of simplicity, since you don't really learn or understand how the internal workings of such a product really function. When writing firmware for a microcontroller, you will usually utilize existing libraries that provide abstraction layers. The terminology and acronyms of these will vary, but I like to think of them as three different kinds. At the lowest level, the Peripheral Access Layer, or PAL, which controls all of the registers of the microcontroller, such as pulling voltage of a pin high or low, or protocols like I2C or UART. Most microcontrollers use memory-mapped registers to control different functions. Memory or RAM is where your code and variables stay, and you can write to it freely, but if you access memory beyond the designated range, it's usually invalid. However, if you check the datasheet for the microcontroller, like the NRF52, you can see where in memory map are the registers. If you write the correct bits to a particular memory address rather than storing those bits like memory usually does, it'll control a hardware feature of the microcontroller instead. The job of the PAL is to provide a function for every single feature the microcontroller supports, and that function flips the appropriate bits in that register. The layer above that is the Hardware Abstraction Layer, or HAL. The HAL exposes a friendly, higher level API for utilizing the microcontroller's abilities like sending data over UART. It usually makes it harder to screw something up because it utilizes idiomatic language features like objects, methods, initializers, and structs. Usually in the real world, when you write custom firmware for something, you are going to be working with an existing HAL for that microcontroller of the hardware. Lastly is the Device Abstraction Layer, or DAL. This abstraction layer is specific to the physical board itself, not just the microcontroller. When you're writing MicroPython code for the microbit, you have the DAL at your disposal to do things like control the LED array to display text with one line of code. This LED array, for example, is specific only to the microbit and not any other PCB that may also use this NRF52. When you're writing firmware for a new piece of hardware, you won't have one of these at your disposal, and at best you'll be working with just the HAL. Homebrew in the computer science world is the act of creating a piece of software from scratch for an existing hardware as an alternative to the software that hardware was originally intended to run. ExpressLRS is an example of a project that originally started as such. Before Chinese manufacturers like Happy Metal started making ELRS hardware, the easiest way to use ELRS was to flash it on top of either an Immersion RC Ghost module or an FrSky R9 module. The ELRS devs reverse engineered the hardware of the R9 and Ghost and wrote ELRS firmware in mind to use that hardware. I'm going to try to do the same here with the microbit on this Airbit drone. The microbit was only ever intended to run CODAL and MicroPython that it ships with. Instead, I'll be writing the firmware in Rust, which is my preferred language. I'm not going to cover a step-by-step programming tutorial, but I will try to provide a skimmed overview of what goes into writing an embedded firmware. In the compilation config, I'm going to set the target to this one here, which corresponds with ARM Cortex-M4 architecture with hardware floating point acceleration. This is the ARM architecture that the NRF52 uses. Next is the linker script, which corresponds directly with this microcontroller. Setting the architecture isn't everything. There's thousands of microcontrollers that use this exact ARM architecture, but they all have their own memory map. During compilation, one of the end steps of the compiler is a compiled object file. This file needs to be passed through a linker. The object file spit out is machine code, however, the memory addresses internally are just placeholders with offsets from a reference base. Different microcontrollers from different brands usually have different memory maps. Here you can see the memory map ranges of this Nordic NRF52 in the datasheet. I've placed these values in the linker script, which tells the ARM linker where the persistent flash and memory ranges start. Now I'm going to add the HAL library for this NRF52 microcontroller. Speaking of which, there is actually a microbit DAL library for Rust available too, but I'm not going to use it to demonstrate my point that if you know what you're doing, it's not necessary. Remember, the DAL is the highest level of abstraction. Rather than being specific to the microcontroller, it's specific to the microbit board itself. If you understand what's going on low level, the HAL is enough. Besides, the dedicated microbit DAL is not very good anyway. It doesn't do much and mostly just exposes the HAL regardless. An essential whenever you're writing bare metal firmware in Rust without an operating system is you'll define these two attributes, no main and no std. Std, or standard lib, refers to the Rust standard library. The Rust standard library is two halves, core and alloc. Core is core functionality such as built-in types and does not invoke system calls, therefore requires no operating system underneath to function. It's the lowest level library there is and is always available. Alloc refers to the runtime heap allocator, which is an operating system specific thing and not available in bare metal firmware unless you specifically set that up. Most of standard lib uses alloc, so most of standard lib is not available, hence the name no standard lib. We do still have core at our disposal, just not alloc. The other attribute is no main. Main is the name of the first function that gets executed when a program runs. This is where your code actually begins. However, main also assumes an operating system is present and that a number of things were set up during runtime before main is ran. In embedded firmware, the microcontroller can have a number of fault conditions and things that need to be specially handled, so it could have a dozen different entry points. These entry points are referred to as the vector table. The vector table is specific to all ARM Cortex-M microcontrollers. It is a sort of low-level exception handler that is baked into the silicon of the chip. The primary one is reset, which will run main, but you do still have to handle the other fault condition vectors when something goes wrong. For example, an instruction that has an invalid opcode will trigger a hard fault. Thankfully, we don't have to do any of that. We simply tack on the entry attribute to any function that we want, and that's now our new main entry point. This easy entry attribute is provided by the ARM Cortex-M runtime library, which sets up the exported symbols for all these vector table entry points. It has its own linker script underneath that places the pointer to these vectors at the beginning of the .text section the way the ARM microcontroller expects it to be. During compilation, this internal linker script is combined with the one we wrote here. That way, the final compiled binary that's flashed to the microcontroller gets read as soon as voltage is applied. The vector table will be decoded at start, and the ARM microcontroller jumps to the appropriate main entry point where code execution begins. Now comes flashing the firmware to see if everything is good up to this point. When we compile our Rust program, the ARM GCC linker outputs the final binary file in ELF format. The Dappling interface chip expects the files you would drag and drop onto it to be in Intel hex format, which I could not find any easy way to convert to. Instead, I'm using ProbeRS, which is an embedded firmware flash and debugging tool for Rust that, among other probes, supports Dappling out of the box. This is just some build tooling which automates finding the Dappling probe connected through USB and flashing the firmware through Dappling to the target NRF52. This is only necessary in these dev boards that have these internal flashing tools such as an ST-Link or Dappling. In the real world, in either a production or even prototyping stage, none of this is necessary since you would flash the microcontroller directly through serial wire debug or similar. Since I'm currently compiling without release optimizations, the compiled ELF binary contains debug symbols. We can load it in a GDB session and connect to the microbit. Now there's a live debugger attached to the microbit, as it's physically running, and I can do stuff like hit a breakpoint, step through lines one by one, dump registers, dump the stack, or see the disassembly. I'd like to share some very detailed resources where most of this information is covered. These are 3 books for writing bare metal firmware in Rust. The first is the Discovery book, which is a guide based around the microbit itself. Although it centers around the doll, which I'm not using, the toolchain setup is universally applicable and it has good examples. The second is the Embedded Rust book, which provides a much lower level guide on how the abstraction layers actually work and how writing Rust on a microcontroller is done. Lastly, and my favorite, is the Embedded Macha-tron, which is the lowest level guide that shows how the Cortex-M runtime actually sets up the vector table and the linker script to support it. If you're like me, these are great reads on the subject of embedded development. If you're normal, however, you'll never touch these. Now we can move on to actually writing code for this. After importing the Hall library, I initialized an instance of the peripheral object. Everything the Hall provides will be provided by this instance. The end goal is to get working communication from the microbit out through the I2C pins into the Airbit's control board. The Airbit control board has a gyro and a forward 1 ESC, which both can be accessed through I2C. To use I2C, we need to set up a peripheral to access that interface. The NRF52 does not actually have I2C support. It instead has TWIM, 2-wire interface, I don't know what the M stands for, which can emulate I2C. That's why we're using the TWIM peripheral instead. Next, we'll define the pins for the I2C SDA and SCL lines, serial data and serial clock. Now here's where it gets tricky. The microbit has a so-called external I2C interface, and in the schematic, we can find the pin out for that is port 0 pin 26 and port 1 pin 0. Try using this interface, you'll never get it to work, because if you look at the wiring diagram, these 2 pins are over here on the edge. On the Airbit, those aren't hooked up anywhere. Instead, the original Airbit code reassigned I2C to use these big pins labeled 1 and 2. Looking at the schematic, these big pins 1 and 2 are actually port 0 pin 3 and port 0 pin 4 respectively. They are simple GPIO peripherals which are reassigned to be our new I2C interface. That's why these are the pins we have to define when initializing the I2C peripheral. Now that I2C is working, let's talk to the control board. Looking at the example source code for the Airbit, I see it calling this gyro initialization function. If you find the source code for the Airbit extension on MakeIt's GitHub, you can see what this function actually does and that it communicates over I2C to the external gyro on the control board. Now I have no idea what this gyro actually is. It's not listed anywhere, however I'm pretty sure it's an MPU 6050 or similar. Looking at the silkscreen text on the chip, I wasn't able to find a datasheet. I do actually have my own MPU 6050 on hand and tried comparing them and the markings are different. However, the registers and addresses in here are exactly that of an MPU gyro, so it's a safe bet. I simply copy the addresses and register variables over and write to the exact same I2C registers as how the Airbit originally did. Here, with these last 2 register writes, we can see some of the secret sauce behind how the Airbit does filtering, and simply enables it directly within the gyro itself. It configures the gyro filter to be a 250Hz low-pass filter and the accelerometer at 10.2 Hz. These filters are built into the MPU gyro itself as a convenience for not having to do filtering on our end in software. The way I2C communication works is first you write the address of the slave to the bus. If the slave peripheral, such as this gyro, picks up its own address, it'll continue listening to the subsequent bytes for the remainder of that transaction. So for example, to set the gyro's filter according to the datasheet, we write byte 0x01, which is the register for the config, and then byte 0x00, which is the parameter that sets the filter to one of the built-in presets. Now with the IMU initialized, the same way the Airbit does it, we can pull the XYZ values out of the gyro. Writing the same I2C registers as the original Airbit extension code did it, I write 67 to read gyro data, and 59 to read accelerometer data. These 2 I2C transactions will yield bytes, so we provide a buffer for the return data to go. The gyro data, for example, is an XYZ value, however, we need 6 bytes in this buffer, not 3. The values returned are 16 bits, so they take up 2 bytes each. This here is just a bitwise operation to combine the 2 bytes in big endian. Take the first byte, convert it to a 16-bit unsigned integer, left shift 8 bits over, then do a bitwise OR with the second byte to combine it with the first. That's our X value. Now we can repeat for Y and Z and X, Y, and Z for the accelerometer. Printing it out, we can indeed see our IMU driver for this air bit works and reacts to the physical movement. Next is the ESC, which seems to be called the PCA. I have no idea what this chip is, but it seems to be a sort of 4-in-1 PWM converter for DC motor ESCs. Here I initialize it in the exact same way the Airbit accession code did it. Something to note is the first I2C write to the PCA's address is error handled and retried if it fails. The PCA only powers on if the LiPo battery is plugged in. If it's not, then we get a no acknowledgement error, then it'll work. After the PCA is configured, we can use it to spin up the motors. Here is the re-implementation of that function, which simply writes the throttle value for the 4 registers for all 4 motors. And here's an implementation demonstrating the motor spinning up in a spiral pattern. And that's about where I'm going to stop with this. Could, with a little more time, I implement a pit controller and the receiver and make this drone actually fly again? Sure. But in the end of the day, it's a wooden toy, and reinventing the wheel isn't going to make this do much more. Ultimately, what I have here is a firmware, not quite a full flight controller, but a firmware written completely from scratch, in Rust with custom drivers, Homebrew flashed onto the microbit, a device that was never intended to run anything more than Codal and MicroPython that it originally shipped with.